What if rain ruled Earth for 2 million years? Not one endless storm, but repeated deluges strong enough to erase feeding grounds and choke coastal seas. Could the first dinosaurs survive while rivers shifted, forests changed, and food disappeared? And how could rain falling on land begin killing animals beneath the ocean? And the real threat wasn't drowning. It was a planet changing faster than entire lineages could adapt. Here's the catch. 2 million years of rain doesn't mean rain every second, everywhere, non-stop. It means something stranger, a long, humid interval in the late Triassic, roughly 234 million years ago. Rainfall surged far above normal, again and again, with drier spells separating the worst pulses. Rivers swelled, wetlands spread, and erosion went into overdrive. Geologists call it the Carnian Pluvial episode. But Pangaea already ran a brutal climate before any of this started. So what could overpower a supercontinent already built for extremes? Picture Pangaea, most continental land locked together, surrounded by the vast Panthalassa Ocean. Along its eastern side lay the smaller Paleotethys, heat built over rock and sand, while thin vegetation clung to whatever moisture it could find. Seasonal mega-monsoons hammered parts of the coasts and southern regions. Mountain belts blocked wet air and cast enormous rain shadows behind them. Because apparently some deserts needed help becoming even worse. Could the animals thriving here survive once drought stopped being the main test? You stand in the continental interior, where heat radiates from bare stone in visible waves. The wind moves, but it doesn't cool anything. It just rearranges dust. Mountains shimmer through haze. Vegetation stays sparse, and reliable water is nowhere nearby. This isn't the lush dinosaur jungle people picture. It's a furnace with occasional survivors. But success in this world guaranteed nothing. The animals thriving here might be the ones least prepared for what came next. And that furnace wasn't empty. One obscure group was just getting started. Dinosaurs, and they were nobody. In what's now Brazil, fossils preserve Styracosaurus, an early dinosaur roughly 7 feet long. That sounds impressive until the weight shows up. Roughly that of a medium-sized dog. Sharing its world was Buriolestes, smaller, sharp-toothed and walking on 2 legs. So, a theropod, not quite. It sat near the base of the sauropodomorph family tree, the lineage that later produced enormous long-necked herbivores. Its teeth suggest a diet that included meat, which makes the family resemblance even harder to spot. Rauisuchians included formidable land predators, while phytosaurs occupied rivers and lakes. Armored atasaurs crossed the ground, and rhynchosaurs and dicynodonts filled major herbivore roles. Dinosaurs were present, but they weren't running the neighborhood. You crouch as a small dinosaur crosses sun-baked ground among larger animals. Would anyone standing here bet on the little dinosaur? Probably not. Dinosaurs had arrived, but Earth didn't care yet. Far across Panthalassa, though, something much bigger was getting started. And why should volcanic activity in a distant ocean matter to animals on Pangaea? Because this wasn't ordinary volcanism. Rangelia was a large igneous province, or lip. That's not just a volcano with ambition. A lip is an immense outpouring of basalt, erupted across a vast area over a geologically short span. The end Permian extinction had one, and the end Triassic extinction would have one too. Coincidence? Rangelia formed as a volcanic plateau in Panthalassa. Its rocks joined western North America much later. Near the lava, the danger was obvious. Far away, the greater danger was invisible. Carbon dioxide entered the atmosphere-ocean system faster than natural processes could easily remove it. Researchers have proposed extra carbon cycle feedbacks, possibly involving methane, though details remain debated. Temperature proxies point to substantial warming, perhaps several degrees Celsius, not a warmer afternoon. A hotter planet. Oceans heated up, air temperatures climbed, and evaporation accelerated. And what happens when warmer air carries more moisture across a supercontinent already famous for monsoons? Warm air holds more moisture, way more, and moves it farther inland. Monsoons gain energy, clouds thicken, downpours intensify, weathering attacks exposed rock, rivers choke with sediment. The dry world balance begins to break. You feel vibrations pass through the ground as volcanic light stains the distant horizon. The air, once bone dry, turns heavy with moisture. Clouds pile over land that seems to have forgotten what clouds are for. Then the rain comes back, and back again. Here's the twist. Pangaea never needed to bury Pangaea beneath lava. Changing the sky was enough. Greenhouse warming intensified the hydrological cycle, carrying the crisis into rivers, forests, coastlines, and seas. The damage wasn't only rising from the ground anymore, it was falling from the atmosphere. The Carnian Pluvial episode had begun. So what does nearly 2 million years of intensified rainfall do to a supercontinent built for drought? It starts moving, grain by grain. Floodplains widen, marshes spread through low ground, and lakes expand inside continental basins. In wetter regions, forests thicken, and peat-forming environments return. Slopes fail, riverbanks collapse, and floods carve new channels while abandoning old ones. Sand, clay, organic matter, and dissolved minerals move downstream in enormous volumes. Water is useful right up until it starts redesigning the continent. You step into a Carnian forest as rain drums on the canopy in repeated waves. Warm mud shifts beneath your feet, and a swollen river bites into its bank. Branches and sediment vanish into the haze as visibility shrinks. Where's the safe route now? Where's the food that used to grow here? Not every region became wet. Some interiors stayed dry, and some may even have become drier. The Carnian Pluvial episode wasn't one global swamp. It was a planet of intensified contrasts, where one habitat drowned while another kept baking. Still, a wetter planet should have been good news for anything already living in water. So how do scientists reconstruct rainfall from 234 million years ago? The planet kept receipts. Rocks preserve shifts toward river, lake, and floodplain deposits. Amber becomes unusually widespread in some Carnian layers. Erosion cuts older rocks, while offshore deposits record more sediment from land. But what does all that runoff actually do once it reaches the sea? Every river carries part of the continental crisis downhill. Freshwater, clay, sand, nutrients and weathering products pour into coastal waters. Suspended sediment clouds the water, and light stops reaching former depths. Fine particles settle across habitats that depend on clear water and stable surfaces. You sink beneath a Carnian coastline as visibility closes in around you. Sunlight fades through suspended mud, and sediment drifts downward across the bottom. Spaces that once offered shelter and feeding room begin disappearing. You can't feel the rain down here. You only watch the habitat stop working. Carbonate platforms declined in several regions. Algae and other carbonate-producing communities faced lower light, heavier sediment, and unstable chemistry. In restricted coastal settings, freshwater input may also have altered salinity. So could a million years of increased rainfall make parts of the ocean less livable? Yes, but not through one simple mechanism. Mud, freshwater, nutrients, reduced light, and changing chemistry arrived together. Conodonts and ammonoids declined, while crinoids, bryozoans, and some algae were hit. A wetter world hadn't rescued marine life. It had carried chaos downhill and dumped it into the sea. The rain fell over continents, yet one of its deepest wounds opened underwater, and on land, the same rule applied. Strength meant nothing if the world stopped supplying food. Extinction didn't arrive in one cinematic afternoon. There was no single moment when every vulnerable species dropped dead. Decline came through altered vegetation, shrinking ranges, disrupted breeding, and fewer animals each generation. Rhynchosaurs had been extremely successful herbivores. In some ecosystems, they were among the most abundant large animals around. Their jaws and teeth worked well on particular plants. But what happens when the menu changes and your entire body is built for the old one? Specialization stops looking like an advantage. As plant communities shifted, their ecological position may have weakened. The exact timing and causes remain debated. Still, most rhynchosaur lineages vanished during the broader late Triassic turnover. Dicynodonts had survived even longer, enduring previous catastrophes into the late Triassic. Some survived beyond the humid interval, while many others declined as habitats and food sources shifted. You return to the same feeding ground across generations. Familiar plants become patchy, floods keep changing the soil, and fewer animals arrive each season. The gaps between sightings grow longer. When does a common species become rare? When does rare become gone? Nothing announces the moment. The world didn't need to kill them all at once. It only had to stop feeding them. And extinction, brutal as it is, does something else. It clears space. So who moves in when the old specialists disappear? Ferns spread through disturbed ground, conifers diversified, and Bennettitalian plants became more important. Forests developed new layers, while wetlands linked rivers, lakes, and floodplains. Every change created a new test involving food, shelter, water, and open ground. Herbivores faced unfamiliar plants, predators followed reorganized prey, and small animals gained cover. Semi-aquatic species found expanding waterways. Evolution didn't pick one winner. It rewarded whatever happened to fit each place. And among the lineages stepping into that newly opened space were animals almost nobody had noticed: dinosaurs. Around and after the Carnian Pluvial episode, dinosaur diversity increased in some regions. Their abundance rose in some formations too. Younger Carnian rocks in South America preserve richer dinosaur communities. Herrerasaurus and Eoraptor shared landscapes with early sauropodomorphs and other dinosaurs. So did the rain create the dinosaur age? Not by itself. Fossil sampling is patchy. Diversification was underway, and researchers still debate the CPE's exact role. But the timing matters. And what happens when ecological space opens while a flexible lineage is already waiting nearby? Opportunity compounds. Some dinosaur groups diversified, became more abundant, or later grew much larger. Dinosaurs weren't the only ones cashing in. Etasaurs remained widespread as plant communities changed. Phytosaurs diversified through river and wetland systems. Great news for phytosaurs. Less comforting for anything sharing the water. Turtles and crocodilomorphs diversified too. Could this ancient climate crisis have helped shape lineages still alive today? Maybe. But the answer isn't simple enough for a victory lap. Rauisuchians remained major predators. The old powers hadn't vanished, and the newcomers hadn't won. You move through a transformed world where dark water hides a phytosaur nearby. An armored etasaur crosses wet ground as small dinosaurs slip through dense undergrowth. Larger predators still control nearby territory. Who's winning? Nobody knows. Every creature is simply better, or worse, matched to conditions that didn't exist before. The rain didn't reward the strongest animals, it rewrote the test. Dinosaurs weren't handed a kingdom, they were handed possibilities. Across thousands of generations, those possibilities compounded. Some dinosaurs spread or grew larger, while rivals adapted, persisted, or disappeared. The contest wasn't over, but the future had opened wider than before. Eventually, Wrangellia's major eruptive pulses waned, and the carbon cycle disturbance eased. The humid interval faded too. Heat and dryness crept back across much of Pangaea. Rivers, wetlands, and forests shifted once again. So what happened when the sky finally cleared? Did the old world come back? Not even close. Rivers changed course. Sediment entered lakes and seas, and marine communities didn't fully reassemble. So no, 2 million years of extra rain didn't just leave Earth soggy and forgettable. Strength matters, but when the planet rewrites the rules, matching the new world matters more. The clouds eventually broke. The evolutionary consequences didn't. If this changed how climate, extinction, and evolution connect, like the video and subscribe for the next Deep Time story. The Carnian rain cracked the door open for dinosaurs, but powerful rivals still blocked the way. When the end Triassic catastrophe removed many of them, would dinosaurs have ruled without that final blow?